So feels like that went too fast. Already talking about exam 4, already halfway through the semester, chugging right along. Okay, so now we're still in the cardiovascular system, right? We've talked about the heart, talked about the blood vessels. Now we'll talk about the actual blood. So we'll have kind of 2 days where we do blood, which is this day, and then the day that will be the TBL day on Wednesday. And then we'll get into the immune system for a couple of days, or lymphatic system. So it's a big chunk of the class in the cardiovascular system, but this is all included in that. So today is primarily, it's kind of an anatomy of the blood, which is not something we think about having anatomy, but it does, right? So what are all the components of the blood? So let's start out with this question here.
Yeah, you guys are so right. I'll agree with that.
It's gonna be bad today.
All right, go ahead and send that in if you haven't yet. All right. I think there's still some more. I only got 39, 40 now. Anybody else? Few people went on spring break early. Let's hope not for the exam Friday. Okay. All right. So about 70% of you are saying C, plasma, which is correct. Plasma is the about 55% of our blood. Most of that is water, but there's some other components in there too. And then red blood cells typically make up about 45% of our blood, which contains hemoglobin. And we'll talk about that. Yeah, so when we look at it like this, if we take a vial of blood like this, put it in the centrifuge and spin it, all the densest, heaviest stuff will go to the bottom, and then kind of less dense as we go up. So all the red blood cells go to the bottom. Get this little layer in the middle called the Buffy coat, and then the plasma is the stuff on top. Okay, so when we talk about hematocrit, this will be something that you guys do in lab. You'll take your own blood. That's actually the lab the week we come back, where you will prick your finger and you'll get some blood in a little tube. You'll plug up one side with some like clay stuff. You'll put it in a little centrifuge and spin it down, and then you'll actually measure with a ruler the amount, the whole thing. You'll measure the whole thing like this, and then you'll measure what percent, or then you'll measure the red part, and then you just get a percentage, and that pretty much is a good way to tell you what percentage of your blood is red blood cells. And that's what hematocrit means, is what percentage of your blood is red blood cells. Okay, typically in males it's about 47% on average, females about 42. The main difference has to do with sex hormones. It doesn't have to do with the menstrual cycle. That's kind of just a common misconception that women lose some blood with the menstrual cycles. Maybe that's why, but it's not that. It's typically more due to the effects of testosterone on red blood cell development versus estrogen are different. And so yeah, so when somebody has a real high hematocrit, it could be due to blood doping, which we'll talk about. If they have a low hematocrit, then this could be a form of anemia, and it could be due to blood loss. So when we look at that top component, that's all the plasma. Okay, so this is the least dense part. It's mostly water. This is about 55% of our blood. That little spot in the middle called the Buffy coat, that is mostly our white blood cells and platelets. So leukocytes are white blood cells, and then platelets are going to be a key thing that helps us with blood clotting. That's less than 1% of the blood. And then the other 45% are the red blood cells or erythrocytes. This is the most dense component. So these are the three main components of the blood. So we'll talk about each of these a little bit today, and about some of the cells we find in the blood, as well as some of the other components. I'll let you finish writing that down. That was too much to have you guys write. I'll do that. Change that for next year. Okay. You good? Got it? Okay. All right. So let's talk about the plasma first. Okay. So the plasma has this kind of yellowish color. Again, 55% of our blood volume, it's mostly water. 90% of it is water. And then about 100 different things dissolved into it. So this includes all of our electrolytes, ions, right? Gases, oxygen, CO2, waste products, nutrients. Gases don't dissolve well in water. And so we typically have special carriers for gases, okay? Like our red blood cells. Those are our special carriers for oxygen. We have a special way that we carry CO2. We'll talk about that in one more when we get to the respiratory system. And then we have plasma proteins. So this is about 8% of our plasma. Almost all of these are made in the liver. And our main one, that the most abundance, called albumin. But then we also have all the things that have to do with blood clotting for us too. Okay, so clotting factors. We'll talk about that's the next TBL day. Talk about blood clotting. And there's a bunch of proteins just floating around in our blood all the time. And all it takes is for them to kind of be activated. And that starts the blood clotting process. So that bottom line has a question of what is serum? Okay, so it's common to hear somebody say like we're measuring somebody's serum cholesterol level or serum glucose level or serum something. And so that's just a common term used in medicine. And what that means is it's the plasma, but with the fibrinogen removed. Fibrinogen is the main protein that causes the blood clot at the end. Okay, so we turn fibrinogen into fibrin at the end of the blood clotting cascade, and that's what causes the clot. So most of the time, is anybody an EMT in here or do that kind of, yeah. And so you may have learned this or may learn this in other hospital observing situations or lab observing situations, but most of the test tubes that are used to collect someone's blood are coated with a certain substance that pretty much grabs onto that fibrinogen and makes it so the blood won't clot because it would clot naturally. So yeah, the bottom line says plasma with fibrinogen removed, and then pretty much it says the blood is allowed to clot, then that fibrinogen is removed, and then it doesn't include the cells either, right? But all the cells are not in the plasma part, they're either in the red blood cell part or the buffy coat part. Questions on that? Need me to read the bottom line again, everybody? Yeah. Yeah, so the first part says plasma with fibrinogen removed. Okay, so it's the plasma with that one protein removed. And then the other part just says blood is allowed to clot, and then the fibrinogen is pulled out pretty much. So it's just kind of the same thing twice. Okay. All right, so then we got the red blood cells, okay? So red blood cells, AKA erythrocytes or RBCs, we have about somewhere between 4.2 and 4.6 million of these per microliter of blood, okay? They're interesting cells because they don't have mitochondria, they don't have a nucleus, and so they can only make ATP via that anaerobic pathway. Okay, that's the glycolytic system or using the one that produces lactate. Okay, they really don't have a lot of function except for the one function that they do really well, which is carry oxygen for us, right? So it's this big bag full of hemoglobin. They have what's called a biconcave shape, which just means there's like an indented part on both sides to it. Okay, and the reason that helps us is it gives those cells the ability to swell and shrink a little bit, and it increases their surface area and makes them flexible too, because they have to squeeze through really tight spaces. Our capillaries are the size to fit one of these red blood cells through at a time in a single file line. And so they have to kind of get smashed and squeeze around through those capillaries to make it through. And so that biconcave shape helps with all of that. Questions on that? Okay. Another clicker question here. So take a guess here. What would you say? How many molecules of hemoglobin are in a single red blood cell? Turn with your team and take a guess, see what you guys think.
1 billion.
Throw your guess in there. No. All right, anybody else? I'll leave it open for a sec. So we got about half of you saying D, about a quarter saying C. So yeah, so D is the correct answer. So it's about 250 to 280 million in a single red blood cell. Okay, we can carry, some of you might know this part, then how many oxygens can be carried in one hemoglobin? 4 O2 molecules are carried in a single hemoglobin. And we got 250 million of those, okay? So then how many molecules of oxygen in a single red blood cell? It's about 1 billion, right? So that would be that one there. So that's a single red blood cell, okay? And then we said we had many million, how much? About 4.3 million red blood cells per microliter of blood, okay? That's really small. A microliter is incredibly small, okay? So when we look at the total count of cells in the human body, there's about 30 trillion cells, okay? Of those 30 trillion, 25 trillion are red blood cells, okay? So the vast majority of the cells in our body are these, by far, right? There's nothing else that even comes close to the number of cells that we have versus the red blood cells, okay? So again, we could take that 25 trillion, times that by 1 billion, still a really big number. I'm not sure what it is, but right. So just many, many, many molecules of oxygen are carried in our blood at all times, right? So when we look at this graph too, yeah, we got in number, our red blood cells are by far the most, but then in weight or by mass, a pretty small amount of mass, right? Only about 2.5 kilograms of red blood cells, which kind of seems like a lot. If you just think of blood, that's kind of a lot of blood, right? But then most of it is our muscle mass and our fatty tissue and yeah, and other things. So yeah. All right, so let's talk a little bit about hemoglobin. So hemoglobin is a functional protein that is inside of all of our red blood cells. Okay. It has 4 polypeptide chains, so 4 strings of amino acids come together, right? They're called the 2 beta chains and 2 alpha chains. Okay, so we can see those there. Each of those has an iron group, or what's called the heme group, in the middle of that, right? So we can see that heme group in the middle of each of those 4 kind of strings of proteins. Okay, and then each of those heme groups binds with 1 O2 molecule. So that's why we get the 4 oxygens per hemoglobin. Okay, so obviously the basic function of our red blood cells is to reversibly bind with oxygen and carry that oxygen. Okay, so we kind of have hemoglobin with the HB there, binds with oxygen, and we get oxyhemoglobin. Okay, and this equation goes back and forth, right? So if the red blood cell finds itself in a situation where there's lots of oxygen around it, and oxygen is going to push its way into the red blood cell, and which way would that make the equation go? right or left? Talk with each other for a second. When the red blood cell finds itself in a situation with lots of oxygen around it, oxygen pushes in. Which way does that equation go, right or left? Just check with each other real quick. You can do it on your clicker. Send in A for right. B for left. Oh, yeah. He's up there after class. I just need to see if you can meet for a different time tomorrow. That's good. So just A or B, go ahead and put that in there. All right. Still a few of you haven't sent it in. I'll leave it open for a sec, but almost everybody, 90% of you are saying A to the right, right? Yeah, so we're going from oxygen not being bound to hemoglobin to oxygen being bound to hemoglobin, okay? So that would be the case in the lungs. That's what happens in the lungs, right? The red blood cells up there in the lungs, in the capillaries around the lungs, there's a bunch of oxygen there because we breathed it in, right? That's going to make oxygen push onto the red blood cell, okay? That red blood cell is then going to get pumped, or it's going to go from the lungs back to the left side of the heart now, right? And it's going to get pumped out of the left side of the heart out to the body, right? And then it's going to go down to, let's say, our legs, right? Ends up in a capillary in our legs. And then there's low oxygen concentration around that capillary, right? So now that low oxygen concentration makes the oxygen come off of the hemoglobin and go into the cells there to use it, right? So it's just all about the diffusion gradient, which is going to cause that, right? So we would just call this the tissues, right? So some version of our tissues, all kinds of different tissues, but that's where we're delivering the oxygen to. Okay. The poisonous gas of carbon monoxide also binds to hemoglobin, and it does it competitively with oxygen, but it has a 200-fold stronger affinity to hemoglobin than oxygen does, right? So if we get too much of that in our system, it doesn't matter how much oxygen we breathe in, we can't get oxygen onto our red blood cells because it already has hemoglobin or already has carbon monoxide bound to it. And so we pretty much suffocate even though we're still breathing, right? Because we can't get oxygen onto our blood. Okay, questions about any of that? Yeah, Ashton. What would make it go to the left? So that would be like this situation here. So when that red blood cell gets pumped down to the tissues that need that oxygen, right? Then that red blood cell's in a capillary and the space around it, we could say we're exercising and it's down by our muscles, right? Those muscles are using up oxygen, so the oxygen concentration is lower down there. So when that oxygen concentration is low around the red blood cell, then that's going to go from high concentration to low, so move out of the cell. And to do that, it has to come off of hemoglobin, right? So that's what would be going to the left. Yeah, good question. Other questions on that? Yeah. Mhm. Yeah, great question. So back to what we talked about with the blood vessels, right? So we've got the arteries down to arterioles over to capillaries, right? So it goes in the capillaries. That's where the exchange happens, right? That's where it's going to drop off oxygen. Then it's going to go from those capillaries, the red blood cells going to go from the capillaries into the venules, right? And then into veins, back to our big vena cava, then it goes back to the right side of the heart, right? So we go atrium, right ventricle out to the lungs, then it can get filled up again. Now we're back to the part where there's high oxygen, the oxygen pushes back in again. Yeah, good question. Other questions on that? Yeah. Yeah, absolutely. We have a red blood cells live for somewhere between 2 and 4 months. Yeah, so we're constantly making new red blood cells and replenishing them, but yeah, they last for a few months. So. Yeah, and our overall blood volume is about 6 liters. And our typical resting cardiac output's about 5 liters, right? So we're kind of thinking about the blood, our whole blood going through our heart about once a minute, pretty much, right? Every minute, our heart pumps about the full volume of blood through our body. So the same red blood cells that were down delivering oxygen to my legs a minute ago are now back at the well, they're back at the legs again, and they already went back and got filled up and came back down. So yeah, and that's just at rest too. During exercise, our cardiac output could go up to 36 liters per minute, right? So then now we're pumping our full blood volume through the heart 6 times a minute, right? So yeah, so that red blood cell would be passing through many times in that minute. So, yeah, great questions. Other questions on that? Okay, all right. So there's some things that can happen in the body to adjust how well the hemoglobin binds to oxygen. Okay, and so these things happen to be related to our use of oxygen. Okay, so the products or byproducts, kind of signs that show us we're doing a lot of metabolism, are things that are going to help the oxygen fall off of our red blood cells easier. Okay, so the 3 primary ones you need to know are high CO2 levels, high hydrogen levels, or higher temperature. Okay, so this is very related to what we just talked about last time with the things that cause vasodilation too, right? Remember those local factors that cause vasodilation? High CO2, high hydrogen. We talked about potassium with that one. We don't have that one here, but temperature as well. All those things happen when we're using when we're doing metabolism, when we're breaking down products to make ATP, right? We make CO2, we make hydrogen, we increase our temperature. So when that's happening, more oxygen is going to fall off of the red blood cell than it would if we didn't have that situation, which helps us, right? Because if the red blood cell is in a situation where there are high levels of those things, that means that area is using a lot of oxygen. So it would then make sense to drop off more oxygen, right? And this is just all about the properties of the protein hemoglobin. When it has some extra CO2 binding to it, when it has some extra hydrogen binding to it, that changes its shape a little bit. So it makes it harder to hold on to oxygen, and the oxygen falls off more readily. Okay, so the other is just the opposite. So for you in the back that think you have to stand up to look at it, don't worry about it. Just flip the arrows. They're all just downward arrows instead of upward arrows. Okay. So the things that are going to decrease unloading or make the hemoglobin hold on to oxygen more strongly would be low CO2, low hydrogen, low temperature. Those are all signs that we're not doing much metabolism, right? So then there's no reason to drop off a bunch of oxygen if we're not using a lot of oxygen in that area. Okay, questions on that? Okay, so how do we produce red blood cells? Okay, so red blood cells are made in our bone marrow via stem cells. Okay, so it's kind of an interesting thing that all the cells in our blood are made inside of our bones. Right? It's kind of this weird setup, really, right? That it's like we have these little factories of blood cell production inside of our bones, right? And the production will increase production when we have things like blood loss or high altitude or exercise, anything that causes a little bit of lower oxygen levels in the blood, that is going to be sensed by the kidneys. Okay, so the kidneys will detect when we have low oxygen. That causes the kidneys to release a hormone called EPO or erythropoietin. And that goes to our bone marrow, stimulates the cells there to start producing more red blood cells. But this process takes a while. It takes 2 to 3 months to kind of get our red blood cell production back up to where it was when we've lost a lot of blood, right? So when you give blood, right, you have to wait like 8 weeks at least, right, depending on the type of blood donation that you do. But I have O negative blood, which means the blood bank calls me every week, but because I'm the universal donor. But I always do a double red cell donation when I do it, which means they pull all your blood out not all of your blood, but they pull your whole blood out. That wouldn't be good. They pull your whole blood out, and then they actually have a machine that spins it down, and they give you your plasma back, and then they keep the red blood cells, and they can take double the amount of red blood cells that way, because that's really the only part they need for the most part with that type of donation is the red blood cells. So, but then in that case, you have to wait 4 months because it takes so many red blood cells, and it takes a while to reproduce those red blood cells. So, yeah. Anybody else? Oh, negative? Yeah. Listen. Yeah, so that's a special type of donation. I've never donated plasma. It is, I think it's a little bit more of a lengthy process. Has anybody donated plasma in here? That one you actually get paid for, from what I've heard. Okay. Okay. Yeah, oh, really? Okay. Yeah. And they usually pay you for that one, right? Yeah. So I thought, yeah, like people kind of like has it like have it as like a side job, like and stuff. But yeah, I don't know the process there, but it is kind of a different, usually a different type of donation center and stuff too. Like the regular blood bank doesn't typically do it. But yeah. How many people have just give blood every once in a while when you get a chance? Yeah. Yeah, it's definitely a good thing. You can literally help save people's lives. And it's actually good for you too. It's actually in improves cardiovascular health to kind of have that stimulus of having to remake your red blood cells and stuff. So yeah. Yeah, so in certain cases, there are people that need like plasma donations, to answer your question a little bit more, Melissa. People that don't have certain types of clotting factors and things like that, and different diseases that limit the number of platelets they have and things like that. When you give plasma, then they can kind of extract those components and donate them to other people too. Is that what you're going to ask, Ashley? Yeah, cool. Yeah. Okay, other questions on that? Okay, so the idea of blood doping, maybe you've heard of this before. It's definitely a thing in endurance athletes. Go ahead and just see what you think about that. What would blood doping do to our hematocrit? Increase it, decrease it, or not change it?
Like, we just took a navigation.
Yeah. Hematocrit. Go back to the one of the first slides we were on there that had the, yeah. So that's the percentage of our whole blood that is red blood cells. Yeah. Oh, you watched that Icarus movie with Dr. Gooden? Yeah. 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 I need to watch it still. He was telling me all about it, but yeah, that's what I heard. All right, go ahead and send in your answer there. What do you think blood doping does to hematocrit? Still about 10 more or so of you. Go ahead and send it in. So the biggest place that blood doping helps athletes is endurance sports, for sure. That term is kind of thrown around sometimes incorrectly. It really means doing something to increase the number of red blood cells in your blood. And so this would definitely increase hematocrit, which is what most of you put. Still like 5 more of you that haven't sent anything in. I'll leave it open so you can do that if you haven't. But yeah, so it definitely would increase hematocrit. The problem with it is it makes your blood really thick. Okay. And so the more red blood cells you have versus plasma, the thicker your blood is and the less easily it travels around through your little tiny capillaries and stuff. And so it puts you at a higher risk for heart attacks and strokes and things like that if it gets too high. The old way to do it was that people would literally just pull like a liter of blood out of their bodies. They would take that, spin it down, just save the red blood cell part, and then freeze it, put it in the freezer for a few months. let your body replenish those red blood cells on its own, and then put those ones you had in the freezer back in your body. So, and you got a bunch of extra red blood cells. So that was kind of the old method of doing it. Okay, it was just taking blood out, freezing it, letting your body recover, and then put that same blood back in. The new method that athletes are doing is with this here, just the synthetic version of EPO, erythropoietin. You can take it as a drug. It's used clinically for people that have a hard time producing red blood cells. It can be a medicine people take when people have anemia, depending on the cause of anemia. But then people can get it illegally too and just boost their red blood cell production, right? So that's kind of the way that most athletes that do it now are using it. Back in the late 90s into the 2010, 2012 era was when blood doping really was a big thing in professional cycling. And so Lance Armstrong, I'm sure a lot of you have heard of him at least, considered, probably one of the greatest cyclists of all time. He won the Tour de France for all those years in a row. It was like 7 years in a row that he won the Tour de France. And then, so this shows who got first place each year, and then who got second place, who got third place. And then this analysis looked back to see once they kind of caught everybody with blood doping, they looked, all the ones in red are ones that were blood doping. So it's pretty much all of them. They were all pretty much blood doping during that era of cycling. And the crazy part is it only really might improve your performance by about 1 to 2%. But when you're at the top of the top, that 1 to 2% is everything, right? That's the difference between who's in the very front of the pack and who's in the back of the pack, right? And so it makes a big difference in that way. But yeah, go ahead.
Like blood doping, when they took out their blood and then went to get diagnosed, and would they be prescribed EPO where they could kind of do like bubble?
Yeah, it's a good question. Now they would probably just that's probably not the only criteria for that. They would need to look deeper and kind of figure out like why they might have it. And so yeah, that's a good question. I don't know if that would happen that quickly. There's probably some other like root cause typically of like why your bone marrow isn't producing. So they'd probably want to try to identify that first before they gave EPO. But I like the way you're thinking. Yeah, it could be a lot for sure. Absolutely. Yeah. And the other problem with that method was like people, sometimes they would get an infection because that blood was just like in their freezer for a while, and then they could die from that, But yeah, Sophia.
So if you had them like low iron, would that mean you have like less red blood cell like turnover or like?
Yeah, it's a good question. So actually in the next lab you guys do, you'll look, actually when you study for that lab quiz, there's a table there that kind of has all the different types of anemia, and there's all different kinds. So you can have low number of red blood cells. That's one. You can have normal number of red blood cells, but low amount of hematocrit inside, or low amount of hemoglobin inside of them. That could be from an iron deficiency. It's like your red blood cells are there, they just don't have enough hemoglobin in them because you can't make it with iron. There's other ones where the cells are too big, cells are too small. So it's kind of a mix of a bunch of things. But yeah, if you're taking in low iron, you may have enough red blood cells, but they just might not have enough hemoglobin inside of them. So yeah, good question. Other questions on that? Okay. All right, so our red blood cells die after somewhere around 4 months, like I mentioned, okay? And they actually get kind of grabbed out of the circulation by cells that are kind of like macrophages, but they're in our liver and spleen. Then they get recycled. The iron part of that is stored in the liver. The heme group, the protein part, is used to make bilirubin. Again, that's just supposed to be an arrow. That bilirubin is stored in the gallbladder, and then it becomes part of what our gallbladder releases with bile. Bile has bilirubin in it, and then all those amino acids are just reused. So sometimes when babies are born prematurely, their skin is kind of yellow like this, okay? And that yellowing of the skin is called jaundice, okay? And the reason you get jaundice is because this bilirubin is building up in your blood, and for some reason your body isn't dealing with it like it should. So it could be that you have liver problems, liver failure, liver malfunction, and the liver's not doing its job of helping to digest that and turn it into bile. And so it builds up in your blood. So we see this in preemies because their livers just aren't fully developed yet and they're not doing their job yet. We also see it in chronic alcoholics too, people with cirrhosis of the liver because their liver is failing. And so their skin starts turning yellow. The whites of their eyes start turning yellow as well. So that's a sign of that bilirubin building up in your blood. Another thing related here is called hemoglobin A1C. Okay, so there's two ways to diagnose type 2 diabetes. One is your fasting blood glucose levels. The other one would be your hemoglobin A1C levels. So hemoglobin A1C is a test that looks at what percentage of your red blood cell, or really what percentage of your hemoglobin is covered with sugar, covered with glucose. How much glucose is stuck to your hemoglobin. And that number can be converted into like a blood sugar number. And that's one of the diagnostic criteria for diabetes. And so it pretty much ends up giving us this like kind of a 3-month average of our blood sugar. So instead of just getting a fasting number with glucose, it's just kind of a one little snapshot of what somebody's blood sugar looks like. If you get that hemoglobin A1C, you get more of a look at how their blood sugar has been controlled over the past few months. I just wrote in 3-month average there on the bottom. So my son Soren has type 1 diabetes, and that's just a thing we always get his hemoglobin A1C because that's a good look for the practitioners to know what his average blood sugars look like over the past few months. All right. Questions on that? Okay, so anemia, we've got some examples here. So the bottom line is for some reason you have reduction in your ability to carry oxygen. Okay, could be because you're not making enough red blood cells. Okay, so this could be a nutritional deficiency. It could also be damage to your stem cell population. That's called aplastic anemia when you can't. So plasticity means like making new of something. So aplastic means you're not making them. So stem cell damage can cause that. That could be the case with chemo, right? When somebody goes through chemo, destroys a lot of the stem cells in your body. And so that's one of the things you have to really watch with chemo is becoming anemic. You could just lose the red blood cells, right? That could be due to bleeding. It could be due to hemolytic anemia, which is a type of autoimmune disorder that makes your red blood cells really fragile and they just break commonly. And so you just don't have enough red blood cells because you've lost them. You could also have plenty of red blood cells, but they're just not functioning properly. One example of that is sickle cell anemia. Okay, sickle cell anemia is just a single amino acid change, changing this amino acid in the 6th position. And it totally changes that hemoglobin protein that under low oxygen conditions, hemoglobin kind of turns into this sickle-shaped rod, really stiff, and it makes your red blood cells do that. And makes them really fragile, and they get stuck in places, and you get blood clots and ischemia in places. And so it's a very debilitating disease. And then thalassemias is this kind of whole group of inherited blood disorders that some of them can affect your hemoglobin production as well, or your hemoglobin functioning. Yeah, Ashton? Discoloration? Hmm. Yeah, I don't know of any diseases that cause discoloration of them. What are you thinking of? Oh, okay. Yeah, so that probably has to do with oxygen binding because that's the idea with when oxygen binds to the heme group in iron is when it actually makes it turn red or even like pink. So like our arterial blood is very bright pink, but then if you look at venous blood, it's more like bluish, right? And so it probably has something to do with that, I would guess. I don't know exactly what would make it look really light, but that is a difference. So if you with an injury, if somebody has an arterial bleed, you'll see the blood looks very different when it comes out versus like what we normally see when blood is coming out of like a cut. It's just like a little bit darker, and that has to do with the level of oxygen saturation. It changes the color of the hemoglobin. Yeah. So, other questions on that? Okay, so this is kind of what happens with sickle cell anemia. is these red blood cells got to get around all these little tough corners and turns. And when they, under low oxygen conditions, like during exercise or other things, they turn into the sickle cell shape and then they get stuck in places. And this leads to pain, can lead to heart attacks, strokes, lots of other problems like that. Okay. All right. So lastly, we're just going to talk about the different types of cells that we find in the blood. Okay. I've already talked about red blood cells. The rest of them are all mostly white blood cells. So we'll talk about some basic types here. And then when we get into the immune system, we'll dive into these a little bit more deeply and talk about how they function. So the most abundant white blood cells, so white blood cells and leukocytes are just kind of interchangeable terms, right? Leukocytes, white blood cells, we can use those together. It's the most abundant one for sure. It's a very mobile cell. It's all throughout the blood, and it's usually the first thing to get to a site of injury or a site of infection would be neutrophils. Okay, they're phagocytic, which means they can engulf other things and kind of eat them, right? They can eat about 20 bacteria before dying. Natural killer cells, we'll see a little video of it here in a sec, but they are big cells that are lymphocytes. Okay, so lymphocytes are cells that live in our lymph nodes. They're mostly in our lymph nodes. That's when they're called lymphocytes. Okay, their main job is to take out cells that are infected by viruses or cells that are becoming cancerous. Okay, they do that by causing the cells to kill themselves, which is apoptosis. They help cause inflammation, but they're not phagocytic. Our mast cells are very important for releasing histamine. Okay, antihistamines that a lot of us take for allergies. Are the histamine part is released by these mast cells. And then we got a couple others, eosinophils, part of our allergies as well, and basophils related to inflammation and allergies as well. Let's watch this little video here on natural killer cells.
Sites with no immunological memory and are part of your innate immune system. Natural killer cells make up about 5 to 15% of the total circulating lymphocyte population. Natural killer cells are called natural killers because they do not need to recognize a specific antigen before releasing their toxins and destroying a virally infected cell or cancer cell. They target tumor cells and protect against a wide variety of infectious microbes. In several immunodeficiency diseases, including AIDS, natural killer cell function is abnormal, thus allowing the viruses to multiply inside of human cells. Natural killer cells kill on contact. The killer cell binds to its target, aims its weapons, and then delivers a lethal burst of toxins that produces holes in the target cell's membrane and creates events that destroy the cancer cell membrane and cleaves DNA into many pieces in a programmed cell death, that is, apoptosis manner. After releasing its lethal package of chemicals, the natural killer cell can detach from the cancer cell and kill many other circulating abnormal cells. Indeed, research has shown that most of the tumor cells that enter the circulation are destroyed during the first 24 hours, and only a few cells succeed in establishing themselves in distant organs from the primary tumor, which is called metastasis. Natural killer cells may also contribute to immunoregulation by secreting high levels of influential lymphokines. Therefore, research to...
All right, we'll stop that one there. But yeah, so some other cells that we that are important as white blood cells would be our monocytes. Okay, so monocytes are the cells that are eventually going to become macrophages. Macrophage just literally means a big eater in Latin. And so they, when they transition from macrophages, they increase in size by 5-fold. And then they can eat a lot more bacteria than those neutrophils. Neutrophils is only about 20. So that's why they were called this term big eater. So they're involved in any attack on a foreign invader, helping clean up injuries, things like that. They also, one of the weapons they can release is called a respiratory burst, which contains a bunch of free radicals. It contains bleach. and even some hydrogen peroxide. All of that is kind of released from these macrophages, and that kind of just destroys everything in the area. These are one of many cells that are called antigen presenting cells, which means they can, if they find something out in circulation that looks like it's not supposed to be there, they'll take that back to our lymphatic system, show it to our B cells and T cells to start the immune response there. So one more video on that one. There's all kinds of cool videos when it comes to the immune system. So let's watch this one too. Well, this is just kind of showing a macrophage hunting around, looking for prey, getting a bunch of little bacteria, taking them in. Once they eat the bacteria, then they release things to activate the immune system. Those are the cytokines. All right. Cool music on that one for sure. Better than the other one, but yeah. So another cell that's important are called dendritic cells. So dendritic cells are actually our primary antigen presenting cell, and they're kind of just roaming around the body, kind of in the tissues, again, looking for things that aren't supposed to be there, looking for foreign invaders, kind of our mobile watchmen. And then again, if they find something that's not supposed to be there, they'll bring that back to the or to the B cells and T cells in our lymph nodes and show them kind of what they found. Platelets are another component of that buffy coat. They're not cells, but they're little chunks of cells. They start as this big mega karyocyte, and that mega karyocyte kind of these little arms that goes out into our capillaries, and little chunks of it come off. And those little chunks are what end up being the platelets. They're very important in blood clotting. Okay, this is the, this is just kind of a little recap of this, all what we just talked about. So yeah, there's just kind of a couple questions for you here. So which is the most abundant overall? Which would be the most abundant white blood cell? And so yeah, this is just kind of recap showing you the function of each. But let's let's have you answer that first question first. And go ahead and talk about each of both the questions together in your team. And I'll just have you answer the first one first, and then we'll do the second one next. So answer this one on your clickers, but talk about both in your team there for a sec. Go ahead and send that in on your clickers. Which letter there is the cell that's the most abundant overall in our blood? And then also just chatting with your team about which one is the most abundant white blood cell. All right, a few more people to send it in there. Make sure you do that, but I'll, yeah, go ahead and since class is about over here. So the most abundant overall, most of you put red blood cells, which is correct. Not even anything else in close to comparison. So way, way, way more red blood cells than any other cell. And then neutrophils are the most abundant of the white blood cells. That's B. So, all right, guys. Study hard for the exam and see you then. All right, see you guys. Bye.